Imagine you're using a cutting-edge reasoning model like Claude Opus or GPT-5. Before it gives you an answer, it thinks, sometimes for tens of thousands of tokens, working through the problem step by step. That reasoning is enormously valuable, both to the company that trained the model and, potentially, to anyone who wants to steal their techniques. So the providers hide it. They encrypt the chain of thought and hand it back to you as an opaque blob, which your client sends back with each follow-up message so the model can remember what it was thinking. Simple, stateless, and supposedly secure. Except it turns out that entire system has a hole in it big enough to drive a truck through, and this paper shows exactly how to exploit it. The vulnerability is architectural. To keep things stateless and cheap, providers don't store reasoning on their servers. They wrap it in what's called an authenticated encryption with associated data envelope, essentially a cryptographically signed and encrypted package containing the hidden thoughts, and they let the client carry it around. For this to work across all the ways users interact with the API, switching models mid-conversation, editing history, resuming sessions, the encryption keys have to be broadly compatible. And here's the crucial finding. Those encrypted blobs are interchangeable not just across sessions and users, but across different models within the same provider's family. Think of it like a hotel where every room key opens every door because the front desk didn't want to deal with the hassle of tracking which key belongs to which guest. That leads to the core attack. Frontier models like Claude Opus 4.8 or GPT 5.6. Sol have heavy safeguards specifically trained to refuse requests to reveal their internal reasoning. But their smaller siblings, Claude Haiku, GPT 5.6, Luna, are optimized for speed and cost, and they don't have those same anti-distillation defenses. So the attacker captures an encrypted reasoning blob from the powerful model, injects it into the context of the weaker model as if it were the weaker model's own prior reasoning, and then asks the weaker model to transcribe its own thoughts verbatim inside some tag-like thinking copy. Because the encryption is compatible across the family, the weaker model dutifully decrypts and reads out the frontier model's private chain of thought in plain text. The safeguarded model is never directly attacked. It's like handing a locked diary to the author's less discreet younger sibling, who happens to have a copy of the key and no qualms about reading it aloud. The authors verify this works by measuring token counts. Since providers bill by tokens, the API-reported thinking token count is essentially ground truth. When they compare that against the token count of their extracted reasoning re-encoded through the same model, the two track each other tightly across 120 Codeforces problems, which strongly suggests faithful, verbatim recovery. They demonstrate the attack against Anthropic, OpenAI, and Google. Interestingly, Claude Haiku 4.5 worked with a single fixed prompt for everything, while extracting from GPT 5.6, Luna required more prompt engineering, best-of-N sampling, and even chunking the extraction into pieces under 50 tokens at a time to slip past anti-distillation filters. From this one architectural flaw, 4 distinct attack surfaces open up. The first is distillation. You can now cheaply build a competitor by harvesting a frontier model's actual reasoning traces, and the authors estimate decoding 10,000 traces would cost around $720 in Haiku API fees. They also show a striking behavioral effect. When they pre-fill Kimi K3 with a short fragment of decoded Opus reasoning, Kimi's subsequent output shifts stylistically toward Claude, sometimes producing nearly identical visible responses. The second attack is jailbreaking. Models are trained to not say harmful things in their outputs, but they're often allowed to reason freely about harmful topics internally, since directly policing the chain of thought can degrade its usefulness for monitoring. So you ask about how to steal cars. The visible response is a benign lecture on immobilizer design, but the extracted reasoning contains the actual attack details. The third attack is where things get genuinely alarming. Developers routinely publish agent session logs on GitHub and Hugging Face for reproducibility, and they often sanitize the visible text without realizing that sensitive information sits encrypted in the reasoning blocks they can't read. The authors scraped 6,708 public trajectories, decoded 315,320 reasoning blocks, and recovered 367 pieces of personally identifiable information and 182 credentials, including 62 real API keys, 33 passwords, and 30 personal emails from genuine user sessions. A recurring pattern is agents being asked to clean up a repository. The agent rereads all the secrets in its hidden reasoning in order to know what to remove, and those secrets get trapped in the encrypted blob forever. 64 of the recovered secrets don't even appear anywhere in the visible chat, meaning the user had no way of knowing they were leaking anything. The fourth attack is prompt injection through poisoned reasoning. An attacker plants a malicious encrypted reasoning block into a public trace, say instructing the model to exfiltrate PowerPoint files to an attacker-controlled server. When another user resumes that trace, the injected reasoning is treated as the model's own prior thinking, and it happily follows instructions that are completely invisible in the plaintext conversation. Long-horizon agentic workflows are especially vulnerable because they're expensive to rerun, so users have strong incentives to pick up where someone else left off. For mitigations, the authors propose several layers. The cleanest fix is moving to a stateful architecture where reasoning stays on the server and the client just gets an opaque identifier, but that costs storage. Short of that, they suggest cryptographically binding each envelope to its originating user, session, and conversation history, hashing those identifiers into the message authentication code so replaying the blob anywhere else invalidates the signature. They also recommend infrastructure-level guardrails that reject cross-model replays, provider-side revocation of suspicious signatures, and targeted refusal training so weaker models learn to recognize and reject transcription attacks. Following responsible disclosure, providers acknowledged the report and patched the specific attacks, so as of August 2026, the exact techniques no longer work. The deeper philosophical point the authors raise is worth sitting with. There's a fundamental tension here. Whatever model processes an encrypted reasoning block must, by necessity, decrypt it internally to use it. So encrypted reasoning can never be more than semi-hidden. The content is always reachable through the model itself, no matter how sophisticated the transport encryption. They also flag that summary faithfulness is questionable. In one AIME problem, the decoded reasoning shows the model stating the correct answer before it even attempts to solve the problem, while the visible summary shows a clean derivation. This raises real questions about whether the summaries users see are honest reflections of what the model actually did. Now let's walk through some questions you might have after hearing all of this. First, why does the weaker model comply when the stronger one wouldn't? The key is that the safeguards on frontier models are specifically trained to refuse requests to reveal internal reasoning, but that training is expensive and mostly gets applied to flagship models. The cheaper models are optimized for latency and cost, and they haven't received the same aggressive anti-distillation training. Because the encrypted blob is compatible across the family, you get to pick the least defended member of the group as your decryption oracle, entirely sidestepping the frontier model's defenses. Second, if the reasoning is encrypted, how does the weaker model actually read it? This is the elegant part. The provider's models all share the same decryption key infrastructure. They have to, because the API needs to be able to accept a returned blob from any legitimate client. When you inject the encrypted blob into a request, the provider's servers decrypt it as part of normal API processing and hand the plaintext reasoning to whichever model is being queried as context. The attack doesn't break the cryptography at all. It just abuses the fact that the cryptographic system was designed for portability rather than for binding a blob to its rightful context. Third, why don't the providers just bind each encrypted blob to a specific user and conversation? They could, and the paper argues they should. The reason they haven't is that tight binding breaks a lot of useful workflows. Switching models mid-conversation, editing history, resuming from a checkpoint, routing across regions for load balancing. Every one of those operations becomes a cryptographic problem if the envelope is bound to the exact conversation state. The providers chose broad compatibility as the simpler engineering path, and this paper is essentially the invoice for that decision. For large-scale recommendation systems, the transferable lessons here are about how caching and stateless design choices can create data leakage surfaces you never intended. Recommendation systems increasingly use LLM-based re-rankers, personalization signals derived from long user histories, and multi-stage pipelines where intermediate representations get cached and passed between services. If you're returning any kind of opaque token to the client, a session state, a user embedding shard, a re-ranker intermediate, and you're not cryptographically binding it to the specific user and request context, you're potentially building the same vulnerability at planetary scale. The concrete recommendation is to hash user identity, session identity, and request context into any authenticated envelope you hand out, even when it feels like architectural overkill. The other practical implication is around agentic recommendation flows and shared training data. If your team publishes agent trajectories, reasoning traces, or synthetic personas for offline evaluation and model training, and many recommendations teams do this to build re-ranker training sets, you need to assume that anything the model reasoned about internally may be recoverable, not just what's in the visible transcript. That changes how you think about PII, scrubbing, credential rotation, and the compliance perimeter of your training data pipeline. The safest posture is probably to strip all reasoning blobs before any dataset leaves the secure environment, and to treat ephemeral reasoning as the default rather than persistent client-carried state.